Over the next few minutes, we are going to discuss a method called variation of parameters. So the general form of the higher order linear ordinary differential equation for the non-homogeneous problem we consider here, this is kind of a mouthful of words. It's higher order of order 2, which is what we have here displayed. So we can call this left-hand side that operator L of y, okay? So is the operator L of y is the linear combination of derivatives up to order 2. And we're going to do kind of two things at the same time. We're going to consider an example, a specific form, and with this example, we're going to illustrate some of the steps in this calculation of calculating the solution of this non-homogeneous problem with this method variation of parameters. But even though we'll be doing this with an example, I want to remind you that many of the steps in this example could be replicated if should we have a more general form of this type. So here is the example. Let's say for instance that with this form we have that the operator here is defined as 1 times y double prime plus 0 times y prime plus 1 times y. So meaning that in that generic general form, in this case p of x is a constant equal to 0, so a constant function of x, and so is q of x also a constant function but is equal to 1. So it's a constant coefficient second order linear differential equation, and then this right hand side here is what we consider that function f of x. In this case is tangent of x. So first let's find a solution, the so-called complementary solution. So we consider the homogeneous problem, and we say, okay, so let's assume that the solution here is of the form e to the rx, which has characteristic equation r squared plus 1 equals 0, and this implies that r is plus minus I. So we could actually write this as 0 plus minus 1 times I, or I times 1. Okay, so those would be the complex roots there on the imaginary axis with 0 real parts, and that means that here the complementary solution, it's something that takes this form, right? So where c1 and c2 are constants, and we're using the real part as the argument of the exponential, and we're using here this number 1 as part of the argument of cosine and sine. So we can write y sub c as constant c1 times y sub 1 added to constant c2 times y sub 2, where y1 is cosine and y2 is sine of x. So this is another way of saying that the complementary solution is a linear combination of cosine and sine. So what we'd like to do next is to compute a particular solution. And remember, this calculation of particular solutions, the way we are learning with these two methods, is something that relies on educated guesses. Okay, so we are going to build or propose a particular solution that is not a wild guess out of the blue, is educated. And so we want to exploit the functions that are part of this linear combination, this y1, y2. We are now going to use that in proposing a particular solution. So we write y sub p be u1, y1 plus u2, y2, where y1 is cosine of x and y2 is sine of x. And you may wonder, well, but that looks exactly like a linear combination as we had before. The big difference here is that this u1 is not a constant. u1 is a function of x, okay? And so is u2. So u2 is also a function of x, okay? So unlike the previous case where you had constants or coefficients there in the linear combination, here this is a special type of linear combination where u1 and u2 are functions. Everything is a function. So really when we write this, we mean u1 of x times y1 of x plus u2 of x times y sub 2 of x. Everything being a function of x. Y1 and Y2 come from the complementary solution. U1 and U2 are assumed to be functions, but they need to be determined. So that is the task, right? So how in the world, how in the world are we going to determine U1 and U2? But let's remember that ultimately what we would like is for a solution Y to be this linear combination of complementary and particular, okay? And so we want this solution, okay? Do we want this solution to be a solution such that the linear operator evaluated at that solution is equal to tangent of x. That's our original problem. Let's remember, going back to the formulation in this example, we want that's the right-hand side tangent of x, right? So we want to come up with a particular solution that eventually will have to satisfy the linear operator, right? And so in this case, the linear operator involves the second derivative, but to compute the second, we need to compute the first derivative. So what we're going to do is that we're going to take a calculation. We're going to compute, we need to compute here the second derivative of this proposed y sub p. So, and I want to remind you that we're basically going through this by doing both the specific example of the linear operator equals the linear operator equals to tangent of x, while also pointing out certain general patterns, okay? So, so that means that I want to write a few extra steps here with the general form of u1, y1, and u2, y2, before I actually stick in or replace or substitute y1 with cosine and y2 with sine. So the first derivative requires, as we were considering, u1 being a function of x, u2 being a function of x, and similar for y1 and y2. The first derivative implies that we need to apply the product rule. We need to apply the product rule twice. So on a second step here, I'm going to group terms just for convenience, u1 prime y1 and u2 prime y sub 2. So this here is u sub 2 prime. I'm going to write those two terms first. I'm not doing anything else other than rearranging these terms, and then I write u1 y1 prime plus u2 y2 prime. So we need to move on and differentiate yet once again, but let's make an observation here. So part of the reason of collecting these terms first is to note that if we impose a condition, our calculations will be a little easier. So if we impose a condition that this first term be equal to 0, when we calculate the next derivative, when we differentiate again, we'll be having 0 here, and we only have to take care of the derivatives of this remainder over there. So let's impose condition, I guess condition 1 or something, let's impose a condition that first term be equal to 0. Okay, before we move on, let's force that condition. Suppose that is equal to 0. So when we take the derivative of y prime, y sub p prime, the derivative of the first derivative, we're differentiating only this term here, which also requires application of the product rule again, right? And so that's how we obtain the second derivative of y sub p. But let's remember that the definition of this problem is such that these functions y1 and y2, okay, y1 and y2 by construction, those functions are solutions of this problem, okay? So in this problem, if we evaluate L of y at y equals y1, that would be equal to 0. And also the linear operator evaluated at y sub 2, that would also be equal to 0. That's exactly by construction. That's you can see here how if the function y1 is cosine of x, first derivative is minus sine, differentiate minus sine, that'll be minus cosine, negative cosine plus cosine, that's 0. And by virtue of the same properties of derivatives, you can easily verify that both cosine and sine would satisfy that linear operator. So we're going to make use of that in here. So remember that, maybe I say this again, this operator means that y1 double prime plus y1 equals 0. And from there, you can say, well, then that means that the second derivative of y1 is equal to the negative of y1. Similar for the same thing applies for y2. So we could substitute those second derivatives of y1 and y2. We can substitute this term by minus y1, and we can substitute this term by negative y2. So that means that by making those substitutions, we could rewrite, we could group terms here and make this look as the first portion of the sum involves first derivatives of both u1, y1, u2, y2, and then there is a second portion here of the sum that has this quantity u1, y1 plus u2, y2. But let's remember, let's not forget that this is exactly what we had defined as, okay, let's see, we had proposed, that's how we started with. We had proposed that the particular solution be u1, y1 plus u2, y2. In other words, a linear combination with non-constant coefficients u1, u2 being constants of x, right? So we're going to substitute that by yp's. In other words, we can write here that the second derivative of this proposed particular solution is u prime y1 prime, excuse me, u1 prime y1 prime u2 prime y2 prime minus y sub p. Okay, so we could move the this negative term, we can move that to the other side of the equal sign and write here y sub p double prime plus y sub p, that should look familiar, equals u1 prime equals to this term here, right? So basically what we're finding is that the left-hand side here now is looking like that linear operator evaluated at our proposed, evaluated at u1, y1 plus u2, y2. That's the left-hand side, and that is equal to this.